Good morning, everybody. I want to welcome you all to this edition of the Potter's Roundtable. This is a continuation of some of the topics we've done before, basically having to do with glaze chemistry. And specifically today, we're going to be talking about understanding glaze recipes.
Welcome to the Potter's Roundtable, a monthly podcast where we share our passion for the ceramic arts and a collection of topics specific to potters. Remember to subscribe so you don't miss a single episode. Enjoy the show.
So we're still talking about glaze ingredients, so let's pick up with a few more. I think you have all these on your list. Fritz is the next item. And a frit is a powdered glass. And these have become more and more popular as glaze ingredients, especially for Cone 6 in recent years, because industry is using them a lot. And basically, it's like you can make a powdered glass of any composition you want, and then use it as a raw material, and it's more reproducible than using a mineral. So industry doesn't like natural minerals because, when you dig it up out of the ground now and then you dig it up 6 months from now, there's no guarantee that that hole in the ground, whatever you're getting out of it, is going to be exactly the same composition. But if they take a bunch of chemicals and melt them together and make a certain composition, they can control it exactly and it'll always be the same. So industry, and so a frit is just a powdered glass. They take a bunch of materials and melt it into a glass and then crush it up and grind it and make it into a powder. That's what a frit is. And they come in dozens and dozens of different compositions. And, I should mention, sort of as an overview, the only reason why we really have any of these materials available for our pottery is because somebody else wants them in larger quantities. Industry wants them. And there used to be some raw materials, for instance, that we could get as potters that industry no longer wants, so we can't get them, because nobody is going to set up business just to supply potters. There isn't enough money in it. So we're basically getting things because somebody else wants them in larger quantities, and they're still available for us to use. And so frits are becoming more popular in industry, and you're starting to see them more and more glazed recipes. Most of the time they're used in Cone 6 or earthenware glazes. You don't need them. Most of them melt at a fairly low temperature. You don't need them in a Cone 10 glaze. So they're very common in earthenware glazes, and they're very common in Cone 6 glazes. And they're just powdered glass of all different kinds of compositions. And I can show you, I think I show you some examples later when we talk about recipes, and they're basically just given numbers. Like there might be a frit that's called 3124, and that's the frit. That's a particular company's name for that particular composition. And after a while, you'll learn to recognize even some of the fairly common numbers for the frits. There are about, I'm going to say 3 or 4 companies that make them, and they have their own nomenclature for naming the frits. So, but they all make about the same range of compositions. So one company's name might be different than another company's name, but they have the same composition. Because again, they're making for industry. So if a company wants a certain composition, they'll all make it, but they might give it a different name. Okay, so you'll see all these different frit names. And frits are great materials. As I say, one of the reasons why industry likes them is because they're uniform. If they wanted instead of using a soda feldspar, they would make up a frit that has the same composition as a soda feldspar, and then it's always the same. And they know if there are any impurities in it, they know what they are. And that way their processing is very reliable. There are certain shortcomings to frits in terms of actually using them. One of the problems is if you have a lot of frit in a glaze, it tends to make the glaze settle out. And when it settles out, it makes this like concrete, you've probably seen it, like concrete on the bottom of the bucket. And that's one of the unfortunate properties of frits, is they tend to form that sludge on the bottom that's really, really gets hard. So you have to put other things in a glaze to sort of compensate for it, to try to make that not quite so severe situation. So they have advantages, but they also have disadvantages. They're also a little more expensive than some of the natural ingredients because now they're a manufactured product. They don't just dig it up out of the ground. So there's a lot of chemistry and manufacturing that goes into them. So they're not as cheap as, say, just feldspar or limestone. But more and more recipes and more people are using them because of the uniformity of them. The next 2 ingredients on the list here, pumice and volcanic ash, that's the same stuff. And I have a couple of pieces of pumice over there that I found on the beach in Mexico. This is basically volcanic ash, And it's when it forms, it has a lot of gas bubbles in it. And in the particular pieces that I found, it's so light that it floats. And so that stuff could have come from anywhere in the world. I found it on the high tide mark on a beach in Mexico. And it literally can float around the world for years until it finally gets washed up on a beach. But and pumice or volcanic ash, again, basically, it's like this obsidian that I showed you. It's basically this similar composition. It essentially is a glaze in itself. It's a naturally occurring glass. So if we want to use it, typically we might add other fluxes to it. It already contains silica, but it probably melts at too high a temperature. So we would add other fluxes to it and a few other things and use it as a component in a glaze. And there are a whole series of glazes that are pretty simple based on volcanic ash. You might have volcanic ash and 2 other ingredients, maybe clay and another flux, and that's it. Because you've got everything. Because this already is a glass, or the pumice is. It's just it melts at a little too high a temperature for us. So you need to add a little more flux to bring the melting point down. Wood ashes. Wood ashes are used as a source of flux. That's the reason why we use them. They don't contain much silica, the glaze former. They don't contain much alumina. We primarily use them because they contain a mix of fluxes. And usually what they contain is a lot of potassium oxide, a lot of calcium oxide, and some sodium oxide. And a little bit of magnesium and a little bit of a bunch of other stuff. Because they're not really pure. And that's one of the reasons why people like to use wood ashes as a glaze ingredient, because you get a lot of variation. And there's a lot of sort of serendipitous things that can happen because we don't know what's in them. And different impurities that can affect the colors. And so you get some nice effects with them. But they're used as a source of fluxes. Talc is a naturally occurring mineral. This is a magnesium silicate. Talc. Magnesium, the symbol actually is Mg, fortunately, rather than some other obscure thing. It's a magnesium silicate. So we use talc. It contains some silica, which we want, but we're using it because it contains the magnesium. Now remember, there was another mineral or another rock that we were using that also contained magnesium? Remember, dolomite? So you might say, well, again, why do we need talc if we've got dolomite? For the same reason, kind of analogous to when we had limestone last night, because this melts at a different temperature, and as a glaze ingredient, it has slightly different behaviors during the melting process than what the dolomite does. So this talc is good for like cone 6 glazes, dolomite not as good for low temperature glazes. So it has different properties as a raw material, even though in both cases, it's the magnesium that we want. Okay? Bone ash is it's not a really common glaze ingredient, but it's used for certain glazes. Bone ash chemically is calcium phosphate. And bone ash, it acts as a flux, but it also does some interesting thing because the phosphorus in the glaze, the phosphorus in the glaze also acts as a glass former. So it gives us some interesting sort of optical effects, some sort of watery effects in the glaze. And it affects other colors. A lot of times bone ash is used with iron in glazes, and it helps bring out certain colors of the iron. Like some of these glazes, I don't know whether you've heard of a family of glazes called tomato reds. They're high-fired cone 10 glazes, and they have sort of a reddish brown, and you put in bone ash to help bring out the red coloration from the iron oxide rather than the brown. And it interacts with the iron, so it's really kind of modifies the color. So it's not a major constituent, it's really kind of part of the colorant or the modifiers of the glaze. And nowadays, bone ash literally used to be made from bones. It was, you'd take bones from cattle and they'd be burned in a furnace, and what was left was mostly, as well as our bones as well, all bones are mostly calcium phosphate. And for a long time, it's made chemically now, so it's not made from bones. I had a class years ago that I taught in Glaze Chemistry, and we were making up glazes, and I had a woman who was a vegan, and she didn't want to use the bone ash. And I had to reassure her that this was chemically produced, and they keep the old name bone ash, but it long since is no longer made from bones, actually. But that's an old name, because that's where it was made. That was the only source of it. The last material I have here, plastic vitrox. This is called a clay. It's a rock, actually, that's mined in California. And this is one of those things, this is somebody who has a mine and they're trying to find a use for it. This is my opinion of it. So we don't need plastic Vitrox. There's nothing unique about it. It's a rock, and it's kind of like potash feldspar. So somebody has this big deposit of it out there, and they advertise, this is great stuff, and you can make glazes out of it. Yes, you can, but it's nothing particularly unique that you can't. And you'll see it in a recipe. But as I say, it's sort of like a potash feldspar in composition. So it's not like it's unique and you have to use it and there's no other substitute for it. But if you like trying strange things and you want to see if you get something different from it, it's worth trying. But and it's not expensive. It's just another kind of dirt that somebody has. So the question is, how do we use this information, all this stuff? Keeping in mind that one of the things is that all these ingredients we've talked about, even though the emphasis has been on the final glaze, these ingredients affect all the properties of the glaze from the minute we mix it up to the point it's firing. So like the properties in the bucket and the ability to dry and whether it sticks to the pots, all the properties that require the performance of a glaze are influenced by the raw materials, not just the final melted glaze. So we can use this information basically to sort of understand as we go, at the different steps, what their effect is. And I thought that's what we'll do. I'll talk briefly through the different steps in making a glaze and show you how some of these things can come into, can influence it. So these are the steps during the glaze processing or making of a glaze. So, and some of these we've talked about before, like you're preparing a glaze batch. So you have a glaze recipe and you're gathering up your ingredients to actually make a glaze, weigh a glaze together. Well, you might come into the situation where you have to make a substitution. We talked about that. So, for instance, if the recipe the recipe might call for potash feldspar, and it doesn't specify any particular brand. So you need to know what are these brand names? What constitutes a potash feldspar, like Custer or G200. So you need to know that, what can I use? You say, well, this just says potash feldspar, and I've got G200. Is that the same stuff? Well, yeah, in that case, that would be okay. So that's where it'd be useful to know that information. The same way is if you had one kind, let's say the recipe, or you had one kind of feldspar, and the recipe called for a different kind, it would be useful to know, okay, well, those are both potash feldspars. Even the recipe might not tell you. The recipe might just say Custer. And so you have to know, and you don't have Custer, so you have to know that Custer is a potash feldspar, and therefore I can substitute some other potash feldspar for it. So again, that's where that might be information. Kaolin, there are lots, and clays, there are lots of different brand names. For instance, I mentioned like ball clays and things like that. And so you can't say that there's got to be always a direct substitution, but in general, for a glaze recipe, one kind of ball clay is going to be as good as the next. And sometimes the recipe will say, like, because the person who made up the recipe might say OM4, because that's what they use. That doesn't mean you can't substitute some other kind of ball clay. But if the recipe just says OM4, that's all they say, you have to know, okay, that's a ball clay. Therefore, I can substitute some other, like I have Pioneer. That's another kind of ball clay. I can substitute Pioneer for my OM4. But you have to know, when you look at the recipe, recognize that OM4 is the ball clay. And then there also might be a case where you have to make a substitution for an ingredient that you don't have, like the recipe calls for petalite, like I mentioned. And you don't have any petalite, but you have spodumene. So you'd have to know a little bit more than what we're going to talk about here, but you could substitute the spodumene for the petalite, but then you have to make another adjustment to the recipe to offset the difference in the composition. And if you were getting into it that deep, I mean, it's not that difficult to do. We can talk about that some other time. But there's another adjustment you have to make in the silica content, because spodumene and petalite, they contain roughly the same amount of lithium, but they don't contain the same amount of silica. So when you put spodumene in, you've got to add more silica to it. You've got to adjust for it. There also might be cases where you can use a different ingredient to get the same oxide. And we've talked about that, for instance. The recipe there's like whiting and wollastonite. We talked about that. Those are both sources of calcium oxide. Well, you can't do a direct substitution, but you could substitute one for the other because they're both giving us calcium. So we can make substitutions like that. Or dolomite versus talc. Those are both sources of magnesium. Now, you would have to make other adjustments to the recipe, but you could substitute one for the other. One of one of the important points that I'm leading up to here is you can make the same glaze from different raw materials. In your handouts, you've got a page that looks like this with this chart on it. And it says chemically identical glazes. And what this is just an example. Here are two glazes with different ingredients that ended up with the exact same chemical composition. Now, they may melt slightly differently because of the different raw materials, but the final glaze is identical. And that's because, I can use different, I don't have to use always the same materials, so I can make the same glaze using different raw materials. The next step in your making your glaze is what I call in-the-bucket properties. And that's meaning, like, you've mixed up the glaze and you've got this wet glaze in the bucket that you're mixing up and you're going to use it to apply to your pots. Well, one of the problems that can happen, or things that can happen with a glaze, you may have seen this. You get a glaze, and as you stir it in the bucket, it seems pretty thick. And as you stir it, it gets thinner and thinner and thinner and thinner. There's a property called thixotropy that you may have heard of. And that property is when you stir something, it seems to get runnier and runnier as you stir it. Then you say the glaze is thixotropic. Well, one of the things that can cause that is a lot of clay in the recipe. So if you're, and this is not necessarily a desirable property if it gets too extreme, because literally if the bucket, we have some glazes, I've seen some that they sit in the bucket and they almost look like pudding. And you put a stick in them and you almost think, you're never going to get this to the point where we're going to be able to apply it. And as you stir it, it seems to get runnier and runnier and runnier. And finally it's fine, it's runny and loose and you can apply it to the pot. But when you start out, it looks like you'll never get it on a pot. And so it can be a problem in some cases. And so, and this is caused by a large amount of clay in the recipe. So you might not, if you see a recipe like that has a large amount of clay, you might go, I might run into that problem with this recipe because of all the clay in the recipe. It might end up being thixotropic, which might give me a mixing problem. On the other hand, you might also have a glaze that settles out really quickly. And one of the things that helps in the bucket, one of the things that helps keep the glaze in suspension and prevents it from settling out is to have some clay in the recipe. This is one of the reasons why we like clay in glazes, because the clay helps keep the glaze suspended. After you mix it up, it doesn't settle out quite so quickly as if there was no clay. So there's a value in having some clay in a recipe. You don't want too much for a variety of reasons, but it's also good to have some in the recipe to prevent the settling. Okay, so now you're going to apply the glaze, and the glaze is going to dry. Well, one of the things that can happen is you might get a lot of cracking of the glaze when it dries. And the problem with that is you've got too much clay in the recipe, or too many fine particles. And the problem is either a lot of clay or a lot of fine particles in the raw materials, they hold a lot of water. And then when the glaze dries, they shrink and they cause the glaze to crack. And the cracking can either cause the glaze to fall off the pot, it can cause the glaze to crawl when it's fired. You might not even see the problem until the glaze is fired, and then the glaze crawled, and it might have been the fact that you had too much clay or too many fine particles in the recipe when you put it on the pot. One of the problems with glazes that makes them difficult to diagnose the problems is a lot of times the problems don't show up until the final firing. And the problems might be something it might be go way back to the recipe, nothing to do with the way you applied it or anything else. The recipe might have some inherent problem that only shows up until you fire it. So sometimes it's hard to diagnose, what happened, and it's not the fault of the firing at all. It might be really the fault of the recipe. So it's a good idea, again, if you're familiar with some of these materials, and I've got some examples I'll show you later on, you can look at the recipe and say, that's too much clay. I'm going to have a problem with that glaze, just by looking at the recipe. Another one, bentonite, I mentioned that's a clay that's added to glazes to help them keep in suspension. One of the problems that can cause is that causes these really gooey, sticky lumps. And especially if you've got a lot of bentonite in a recipe, you've got to make sure that the bentonite is really, really well mixed and you've broken up all those lumps, or you'll end up with white spots in your glaze. And the white spots are the little bentonite lumps with none of the other glaze ingredients in the lump. All I've got is a little lump of clay, And it's very you'll see little white spots on your final fired pots, and typically they're dull. They're not shiny like the rest of the glaze, and that's because the bentonite didn't get adequately dispersed. So if you've got a recipe with bentonite in it, you've got to remember, okay, I've got to really be careful to mix this glaze thoroughly. I can't be quite as casual as I might with some of the glazes, because I've got to really disperse the bentonite, or I'm going to have problems. So now let's talk. So now you've applied the glaze, and now we're talking about like the firing. You're going to fire it, and the firing temperature and the firing range. One of the things that I alluded to a little bit so far is different fluxes melt at different temperatures. So actually, when you start talking about fluxes for glazes, there's a family of fluxes that you tend to use for low fire glazes, and then there's a family of fluxes that you use for mid-range, and a family of fluxes that you use for high fire or cone 10 glazes. There's some overlap, like whiting. You can use whiting at cone 6 and you can use at cone 10, but there are definitely sort of groups of fluxes that you use for different temperatures, because that's where they work. That's where they become effective. That's where they start to melt. So for example, nepheline syenite, sodium feldspar, and potash feldspar. Those are all fluxes, and they're similar. Nepheline syenite melts at a little lower temperature than sodium feldspar, which melts at a little lower temperature than potash feldspar. And it's useful to know that. So nepheline syenite melts a little lower temperature than soda feldspar, which melts at a little lower temperature than potash feldspar. So for example, if I have a cone 10 glaze that has a lot of soda feldspar in it, and it's a little runny, one of the things I can do is just change the soda feldspar to potash feldspar, and it'll melt at a little higher temperature and not be quite so runny. And these aren't hard and fast rules, but so it's fairly common to see cone 10 glazes that use a lot of potash feldspar, and cone 6 glazes would be more apt to use soda feldspar, and nepheline syenite is very common in cone 6 glazes, because it's, of those three, it melts at the lowest, and so it's appropriate to use that for a cone 6 glaze. And I also mentioned another example is like whiting versus wollastonite. Those are both sources of calcium oxide. Well, the whiting basically doesn't melt at all. It breaks down, but it actually never melts, and at really high temperatures, cone 10 and higher, it reacts, whereas wollastonite melts. So typically, you'll see wollastonite used as a flux for cone 6 glazes, and you'll see some whiting in cone 6 glazes, but more commonly, you'll see whiting for cone 10 glazes. So you'll see wollastonite for cone 6, whiting for cone 10, because they melt at different, they have different melting properties. And the whiting is generally more effective as a high temperature flux. So that's something else to keep in mind in terms of the melting temperatures. Okay, so you have a glaze, you fire a glaze, and you have, what do you do, for instance, if you have a runny glaze? Well, a runny glaze, meaning you heat it up and it's running, dripping, running off the pot. So what that means is you probably don't have enough stabilizer, right? Because that's the role of these three groups. That's the role of the stabilizer. So one of the first things to try to think about with a runny glaze is add some clay. Add a little bit of clay to the recipe, because with the clay you're adding aluminum oxide. That's a stabilizer. So that's going to help with the runniness. Now I can't tell you how much. This is where you have to do testing. The catch here is that when I add the clay, I'm going to affect some of the other properties. So yes, I may solve the running problem, but I might affect the color, or I might affect the transparency of the glaze. So this is where you need to do testing, so that if you have a glaze that you love, you say, I love this glaze, but I've got to solve this running problem. Well, you might be able to solve the running problem just by adding clay, but that doesn't mean that you're not going to affect some of the other properties as well, because these things are all interrelated. Okay, but that would be at least the first start, is you could add some clay to it, a little bit of clay, and that'll help solve some of the running problems. One of the other things that related to runny glazes is that it's a general rule in a glaze, and this is something to be aware of when you're looking at a recipe, is that you generally want a mixture of fluxes, not just one flux. Because one flux tends to melt or become effective over a specific temperature range. Well, if I want a glaze that's a little less sensitive, and I want to have a wider firing range, then I want a mixture of fluxes. So that I want it, when I heat up the glaze, one flux starts melting, and then as I heat it up a little hotter, another flux starts melting, and I heat up a little hotter, another flux starts melting, and it broadens the range of the glaze, the useful range of the glaze. If I have one flux, when I heat it up, when that flux melts, if I heat it up a little higher, it's overfired. And if I don't heat it up enough, it's underfired. So I end up with a very narrow firing range on the glaze, which is a lot less useful. Like I say, I have a glaze that I can go from cone 6 to cone 14, and it's got a range of fluxes in it, and it's very, very tolerant of range. Well, that's an easier glaze to use, rather than having a glaze that I've got to hit it right on the money, right, within a cone, or it's under or over fired. So in general, it's better to have a mixture of fluxes, 2 or even 3 or more in a recipe, rather than just one. So if you look at a recipe and you see only one flux, that's something you think about, right? The first thing to think of is, I may have a narrow firing range. This may be a more temperature-sensitive glaze because I've only got one flux. And when that flux melts, that's it. Okay, well, and again, I've got some examples of this. That way I can point it out. Crawling. This is the defect where the glaze tends to, when it melts, it tends to part and pull aside, and so you see areas of bare clay or almost bare clay with islands of glaze, and they could be irregular shaped islands. Or I have a great example of a pot in my collection. I only collect bad pots, and I have a great example of a pot where the glaze has crawled and it's slid down the whole wall of the pot. So one whole side of the pot is bare, and the glaze is all collected at the bottom, basically. And that's an extreme example of crawling. It's a great example because it has 3 things wrong with the pot. It warped, and it cracked on the bottom, and it crawled. It's beautiful, yeah. So, great. So crawling generally is due to either too much clay in the glaze or a lot of fine particles. If I'm using a raw material that's been ground to a really, really, really fine powder, that can also cause it. Or if I have a pacifier, there's a category of materials called opacifiers that you add to glazes to make them opaque purposely. If I have too many opacifiers, that can make the glaze crawl. And so, again, this is something where if I look at a glaze recipe and I see that it's got a lot of clay, I can just look at the recipe, I don't even know anything, and just say, I might have a crawling problem with that glaze because it's got a lot of clay in it. So again, there's a lot you can tell just by looking at the recipe. At least I'd say, I'm going to be careful when I use this one or I'm going to apply the glaze thinner or take some precautions because it might crawl. Just looking at the recipe, it might crawl. Crazing. Everybody know what crazing is? The formation of the fine network of cracks. Crazing is generally caused by too much sodium in a glaze. Sodium tends to, when you have sodium in a glaze, it tends to make the glaze contract a lot when it cools, and that's basically the cause of the crazing. The glaze contracts a lot. So if I have a glaze that has a lot of some fluxes in it that contain a lot of sodium, I can just look at the recipe and say, that glaze is probably going to craze. Like if I see a glaze that has 20% nepheline cyanide is a source of flux and specifically sodium. So if I look at a glaze, and if it's got 20% nepheline cyanide, I can just say, I can guarantee that glaze is going to craze.
We hope you're enjoying the show. Please take a moment to leave a 5-star review on your podcast platform of choice. It really helps new listeners find the show. Don't forget to subscribe to receive updates as new episodes are released. And if you'd like to support the video and podcast production of the Potter's Roundtable, become a patron. Go to patreon.com and search for the Potter's Roundtable. Your support will help us achieve our goal of creating a digital library spanning the ceramic arts for use by educators and artists alike. Thank you for your support. Now let's get back to the show.
Okay, color results. I think I mentioned earlier that when you put in a certain colorant in a glaze, the actual color you get can be affected by the flux that you have in the glaze. With the same colorant, different fluxes give different color reactions. Now, it's not drastic. It's not like orange will turn into blue, but greens especially and some other colors are very sensitive. So depending on what the flux is, you could get anything from a turquoise green to a yellow green to a blue green, depending on the flux you use. And so if I have 2 glazes that look pretty similar, and one has mostly sodium as a flux, and another has mostly lithium as a flux, if I put in the same colorant, I won't get the same shade of green. I might still get green, but it won't be the same shade. And as I mentioned, your eye is really incredibly sensitive to differences in color, and you'll see that. So the flux has an effect on color. You don't necessarily put it in there for that reason. You put in the flux or the fluxes to get a certain melting temperature and a certain melting range. But know that it will affect the color, depending on what's in the recipe. Yeah.
Is there any way to counteract that by putting in more colorant or less colorant?
You're still going to change, it's a fundamental chemical reaction. You're going to change the sort of the tint or the hue that you get. Glassy versus matte. The choice of a flux can also affect whether the glaze is glassy or matte. It's not the only thing, but it's one of the things. So, for instance, you might, this is where you can tell, you might have like matte glazes, a true matte glaze is matte because you've produced crystals in the glaze. That's really why the glaze is matte. A true, properly made matte glaze is matte because it's crystallized and the crystals give it that matte appearance. Well, if you have a glaze, for example, that contains a lot of sodium and it says it's a matte glaze, it's not going to be a matte glaze. You look at the recipe, and I've seen this in books. It says, white matte, and it's got a lot of sodium in it, because sodium will not allow you to form crystals, so there's no way you're going to get a matte glaze out of it. So it's simply, I can look at the recipe and say that's a bad recipe. Because there are certain one of the fluxes, like calcium and magnesium and lithium, will give you crystals and will give you a matte glaze. And other fluxes, like sodium and potassium, they won't allow crystals to form. So there's no, if you put those in a recipe or they're in a recipe, you're not going to get a matte glaze because they won't allow crystals to form, and it's the crystals that make the glaze matte. Okay, and the last thing on this particular point was like whether the glaze is truly transparent or whether it's cloudy and opaque. And that also has to do with the balance between the different components, the fluxes, the stabilizers, and the glass formers. And sometimes also you can look at a recipe and you can look at it and say, yeah, that's going to be a nice clear glaze, or no, there's no way in the world that can be a clear glaze, in spite of what the title of the glaze says. So again, all these things, and I'll show you some examples, but all these things with some practice and some familiarity with the ingredients, you can look at a recipe and there's a lot you can tell without just going beyond that, without going beyond the recipe. Okay, so let's look at some recipes. I think I have a page that's titled, Let's Look at Some Recipes at the top. And it says, glaze recipes don't have to be complicated. Okay, well, these are just some examples for different reasons and to make different points. But here's this first one is a cone 6 base. Now that means that's a cone 6 base glaze without any colorants or things added to it. Everybody have the page? Okay, so here's a typical glaze, 5 ingredients, Custer feldspar, ferro 3134, that's a frit. Wollastonite, that's that mineral, silica, and EPK, that's a kaolin, that's Edgar plastic kaolin. And somebody has been fooling around with this to make it so that all the ingredients are 20%. There's no good reason for it to be 20%, but they've been fooling around with these materials to make it look 20%, okay? So in this recipe, I've got 3 sources of flux. The Custer is a source of flux, the ferro, the frit, and the wollastonite. Those are all fluxes. So when I look at this recipe, I go, that's a good thing. I've got 3 different kinds of fluxes, so it means it's probably not going to be a glaze that's going to be super temperature sensitive. That's a good thing. And I've got the silica, which is my glaze former, and I've got the EPK, the clay, that's my stabilizer. So this is a really simple glaze, and yet it has, just looking at the recipe, I can say it probably is a pretty good base. Also, I know I'm looking at this, and none of these materials is highly colored. So this is going to be a clear, uncolored glaze. There's nothing in it, it's going to melt completely. There's nothing in it that's going to make it opaque. There's nothing in it that's going to make it colored. It's just going to be a nice clear base glaze. And then I could put things in it. I could put colorants and things in it.
Glossy?
Probably glossy, yeah. Here's the next one. This is one I mentioned, like a volcanic ash base. This is cone 6. This is slightly translucent, and it contains 40% volcanic ash, 30% whiting, 20% flint, and 10% kaolin. So the volcanic ash and the whiting, those are providing fluxes. And the volcanic ash is also providing some silica along with the flint. And the kaolin is providing some aluminum oxide. So I've got all my 3 groups again. In this case, I've got 2 sources of flux, plus the silica, plus the clay. But now the volcanic ash is a really complicated natural material. So it itself probably contains several different fluxes. It probably contains some sodium and potassium and magnesium and calcium. So it's not a single material. So again, I look at this and I say, this is probably a pretty good glaze. I've got several different kind of fluxes. I don't have a huge amount of clay. 10% kaolin or 20% is not an enormous amount. So this is probably a decent base in terms of its performance. And it's called translucent only because the volcanic ash does contain some impurities, and so it's probably maybe not going to be a perfectly water-clear glaze, that's all. Next one, here's another cone. This is cone 6 to cone 8. It's called glossy transparent base. Gerstly borate, there's that boron dirt, and kaolin and silica. So I've really only got one flux source here, Gerstly borate. I've got the kaolin is my alumina, my stabilizer. I've got the silica and I've got Gerstly borate, and the Gerstly borate contains a lot of calcium and a lot of boron. So in a sense, I've got two different fluxes, but I've only got one source. Now, one of the things if you become familiar with Gerstly borate, which I didn't talk about before, Gerstly borate, one of the impurities it contains clay in itself. And if I have this much Gerstly borate in a glaze recipe, it does two things. It means the glaze is going to be thixotropic in the bucket because it's got enough clay in it where it's going to be kind of this pudding consistency. And it's also, the chances are, it's either going to crawl or it's going to crack when it dries. Because it's got a lot of Gerstly borate, which with a lot of clay, which is going to shrink when it dries, and therefore it's going to crack on the pots. So I may just get cracking of the dried glaze, but that may also cause crawling in the firing. And again, just the minute I look at it, I say that much Gerstly borate, that's going to be a problem. It may melt. It melts just fine. And this is a transparent glaze. It's a pretty good base, but it's the handling problems that I don't like. It becomes thick. It becomes sticky in the bucket, and it may cause cracking and crawling. And that's because I know that Gerstly borate contains a lot of this fine clay, and therefore it's going to shrink a lot when it dries. Okay, any questions on that? Next page, I've got a recipe that says Overcomplicated cone 6. People over the years, and you may see a lot of these out there, they get a glaze and they start fussing around with it, making changes, and if they don't know what they're doing, or even if they do know what they're doing, they make unnecessary changes, and you'll see a ridiculous recipe like this. There's no reason, the recipe below it is the original Randy's Red base glaze. They claim this was a modified Randy's Red. This is the original Randy's recipe below. F4 feldspar, that's a soda feldspar. Here's another good example that I didn't touch on before. F4 is a soda feldspar that's no longer available. So you might see a recipe that just says F4, 20%. Well, first of all, you have to know that means that's a soda feldspar, and also the fact that you can't get that anymore, so you have to substitute some other soda feldspar for it in the recipe. So it's got flint EPK, it's got some Gerstly borate in it. So at least now it's not only Gerstly borate, I've got Gerstly borate and feldspar. So that's better, that's a better situation. And it's got talc, which is a little bit of magnesium, giving me a little bit of magnesium. So I've got, once again, in this recipe, I've got three sources of flux. I've got the feldspar, I've got the Gerstly borate, and the talc. Automatically, that's kind of a comforting thing to know. I've got more than one kind of flux. So that's the original recipe, and this thing on the top is what somebody has done to it. And frankly, when I look at it, I don't even know why they've done some of these things. I don't know what it's supposed to look like. Like, for instance, it's got, let's look at the top one. Custer feldspar, so that gives me potassium. Flint, that's the silica, that's okay. 3124, that's a frit, which is not too different than the Gerstly borate, but okay. Now I've got soda feldspar in there, so why do I need soda and potassium? I don't know. Ball clay, that's okay, but that's a lot of ball clay. Barium carbonate, I don't know why that's in there at all. Barium is generally added as a colorant modifier, and it generally, in some cases, it can intensify a color, but in this case, I'm not sure why you'd need it in there. Gerstly borate, I've already got 3124 and the other stuff, so they've got, it seems like they've got, and whiting, they've got, and dolomite, they've got all these things in there that it's like, I don't need them. Why do I need all this stuff? So when I found this recipe, there was no description as to what the glaze was supposed to look like. Why, what justified all the, I think somebody's been tinkering with it. The other point to make here when you look at this is there's no reason to carry percentages out to 2 decimal places. Even on something that's ridiculously complicated, you could probably round it off all to the nearest percentage and it would be just as good. So there's no reason to have like 19.23%. Call it 19%, it's probably close enough. But this is a good example of, I can't even explain why somebody, and there wasn't in the reference, there wasn't any indication of what all these things are doing. And I know what they do, but I don't know what they do in this particular glaze. Like, why did they end up with this one based on the original one? I have no idea. And yet you see recipes like this out there. And if you ever, I don't know whether if you're ever in the mood for experimentation, if you like doing this sort of thing, is take a recipe like this and take something out and fire it and see if it make the recipe and then start taking things out of the recipe and see what happens to the recipe. In a lot of cases, I'll bet you could probably take half of these things out and you wouldn't see a noticeable difference. One of the other things I found in a lot of glaze testing is that people will make up a recipe and test it and get a certain result, and they'll claim that it was due to the change that they made without considering that it could have been due to something entirely different. Like maybe they fired the kiln, especially with gas kilns or wood kilns. They fired the kiln differently, and that's what caused the difference. So they don't do the controlled experiment where they fire it, they make the old recipe and the new recipe and fire them side by side so you can go, aha, see the difference? They just say, oh, I remember when I fired it last time, it looked like this, and now it looks like this. Well, maybe it was the firing that changed it. Or maybe it was the source of one of the raw materials. Maybe they changed the feldspar source in between that. And so that changed it. So there are a lot of other things that go into it. But anyway, so this is a good example of a bad recipe. Okay, so this is a really old, this is one of Bernard Leach's old recipes. It's a classic cone 10 glaze. And again, it's really simple. They don't have to be complicated. Feldspar, 40%. In this case, he doesn't even care what kind of feldspar it is, just feldspar, 40%. Silica, 30%, whiting, that's the limestone, and kaolin, 10%. And regardless of what feldspar you use at cone 10, you get a nice clear glaze. Now, it may melt a little differently if you use the soda versus a potash, but you get a nice, clear cone 10 glaze, transparent glaze. It's a classic old recipe. It's been around forever. So then you could take this base glaze, and then you could add an opacifier. That's something that makes the glaze opaque. And that could be like Zircopax, which is a commercial opacifier. That's Zircopax, Zircopax. It's actually a mineral. It's zircon. You may have heard of zircon as a substitute for diamond. Well, if you have one at home, grind it up and you can use it in your glazes. When you grind it up, it makes a white powder, and it makes a powder that it doesn't dissolve in the glaze, and so it stays white. So you add Zircopax to your glaze, and your glaze turns milky white. So I can take this clear base glaze and add 10% Zircopax, and I've got a really nice, glossy, opaque white glaze. We used to call it toilet bowl white because it's a really nice glaze, really nice. Or if I take the same base glaze, which is a clear glaze, and I add a little bit of iron oxide to it, and I fire it in reduction, I get a celadon. And this is the basis of a lot of the classic Asian green, pale green celadon glazes as a base glaze similar to this, and just a little bit of iron, meaning like 0.5% or 1% of iron, and you get these beautiful pale greens, apple greens and yellowish greens colors. This is a classic, simple cone 10 recipe. So the real point is glaze recipes don't have to be complicated. That's one of the points I wanted to make. So then there's another family of glazes called Chinos, cone 10 Chinos. And this was one, and again, here's a really simple recipe. This particular one was called PK Chino. And this is just 2 ingredients, nepheline cyanide and ball clay. That's it. Now, I could add, and then you'll see, and there are dozens and dozens of Chino recipes out in the literature, cone 10 Chinos. And Chinos were intended to be fired primarily in reduction to get all the classic characteristics. But there are other recipes where, in addition to the nepheline cyanide and the ball clay, you might add, which is what I've got to the right, you might add sodium or potash feldspar, or you might add spodumene, which is adding lithium, which would give you variations on it, but they still give you a Chino. Then you could add soda ash to it, which is the arrow going down, and if you add soda ash, now you get into the family of carbon trap Chinos. And here's a classic example of a carbon trap Chino. This is called Malcolm Davis No. 1. Malcolm Davis was a potter who was really well known for his development of carbon trap Chinos. And so here's nepheline cyanide, soda feldspar, ball clay, EPK, and soda ash. That's it. Now I can look at this recipe. I think I've indicated on your copies here. When I see nepheline cyanide 45% and soda feldspar 11, that means it's got so much sodium that I guarantee that glaze is going to craze. Just by looking at that. Because that means I've got so much sodium for the neph-cy and the soda feldspar that the glaze has to craze. Not necessarily bad, and especially for Chinos. Chinos are almost regarded because of their defects. They craze, they crawl, they split, and everybody loves it. Well, not everybody, but I can look at this and say, I know that's going to glaze. The other thing to be careful about when you look at this recipe is the soda ash, when you add that much especially, it's very caustic. So if you have sensitive skin, I mean, normally, with most glazes, you can dip your hand in or your foot in and stir them with your hand. There's nothing in most glazes that's going to hurt you. But the soda ash is so caustic, it's actually going to eat your skin. And I don't know whether you've ever felt anything where you dip your hand in something caustic and it feels kind of slimy. It's slimy because the caustic is actually making soap out of your skin. It's turning your skin into soap. And so you're feeling the human soap that you just made. That's why it feels slippery. You've actually made soap out of your skin, out of the oil in your skin. So it's very caustic. So if you're making up this recipe, you want to be careful. Like, you definitely don't want to splash it in your eye. And you don't want to, if possible, especially if you have sensitive skin, you don't, because you could actually get a chemical burn on your hand from the soda ash, because it is caustic. So that's, again, looking at the recipe, I can tell two things. I can say, well, it's going to craze, and I better be careful when I mix it up because of the soda ash. Okay, next page, we've got a basic cone 10 ash glaze recipe. Couldn't be much simpler. Hardwood ash 50% and red art clay 50%. And if you're interested in playing around with ash glazes, this is always a safe composition to start. Some kind of wood ash and any kind of clay, 1-to-1, and you'll get a glaze. It may not be what you want, it may not be pretty, but you'll get a glaze. And then you can play with it from there in terms of modifying, changing things, adding things, changing the proportion, changing the clay, but that will give you a glaze. Really simple. Okay, here's another variation on things we're talking about. What about if you want to convert a cone 10 glaze to a cone 6? What would you think you'd have to do to a glaze to convert it, to make it a cone 6 glaze out of a cone 10? Add more fluxes, and or maybe different kinds of fluxes. So but in this case, we've just changed the proportions. So here's a cone 10 celadon, again, potash, feldspar, whiting, kaolin. In this case, it's got dolomite in addition to the whiting, which gives me a little bit of magnesium, and the red iron oxide. So now if you look across to the cone 6, I've increased the potash feldspar. That gives me a little more potassium oxide. I've increased the whiting. That gives me a little more calcium oxide. I've decreased the clay because the clay is what's going to make it stiff, right? Well, if I'm going to melt at a lower temperature and I have too much clay, it'll be too stiff. So I've cut down on the clay a little bit. I've cut down on the silica, because silica, remember, by itself melts at a high temperature. So if I want this to melt at a lower temperature, I've got to reduce the silica a little bit, which I have. I've increased the magnesium a little bit, another flux, and I've kept the iron the same. And by making those changes, this will now melt, give me essentially an identical glaze, but a cone 6. And I didn't have to change any of the ingredients. I just moved the proportions around following what I know. I need more flux, I need less silicon, and I need less stabilizer. This is a really simple example. I didn't have to swap any ingredients. I just made the appropriate changes in the balance of them. Okay? Here's next page, I've got examples from Brit. And what I wanted to show you here was how, one of the points I wanted to make with this comparison, it's 3 columns across the top. There are a lot of glazes out there that have different names, and in fact, the bases are very similar. So when you look and you say, oh, there are thousands of glazes out there, there really aren't. There are a lot of them that are very similar, and they've changed the name. And I've seen glazes where somebody gets the glaze and they use it, so they change the name. And they give it to a friend and they change the name. And all these things come back into the literature online. And if you really look at them, they're not that different, and they're not even acting that different. And this is an example. So this is from Brit's book on mid-range glazes, and I pulled out 3. Clear, VC, that's Val Cushing Transparent number 3, and one glaze called Easy E Clear. And if you look at it, the glazes are very similar. So what I did here was like the clear has Custer, and so does the Val Cushing have Custer. It has a different percentage, but it's Custer. Well, okay, well, instead of Custer feldspar, the Easy Clear has nepheline cyanide. Very similar. The only difference is the nepheline cyanide has a little more potassium, whereas the Custer has a little more potash, but it's not that different. They all have silica. The clear has wollastonite, that's a source of calcium. Well, in the other VC, instead of using wollastonite, they use whiting. That's still just a source of calcium. And then the Easy Clear used wollastonite again. So they're all still just using calcium oxide. No difference there. They all have kaolin. Clear has a Frit 3134. Well, 3134 is a Frit which is essentially identical to Gerstli borate. So Clear has 3134. VC transparent number 3 has Gerstli borate. Easy Clear has a slightly different Frit, but it's still basically calcium and boron. It's not that different. And then they all have bentonite 2%. So the point is, here are three glazes that they may melt a little differently, but they're not going to be that drastically different. These are only the bases now, because there's no colorants in them, but they're not going to be that different when they're fired. And yet, on the surface of it, especially if you didn't see them side by side, you might see I've got 3 different recipes. I really don't. I've got one recipe with slight variations in the raw materials. So then I could take any one of these 3 recipes, for example, that's what my little arrow indicates, and if I wanted to make a white glaze out of it, I could add one of these opacifiers, tin oxide, or titanium oxide, or Zircopax. All of those chemicals, they're basically white powders. When I add them to the clear glaze, they make it opaque white. And I could add a little bit and make it kind of translucent and milky, or I could add a lot of it, maybe say 10%, and I could make it as absolutely opaque white. Like I say, what we used to call toilet bowl white, just a nice, perfectly opaque, shiny white glaze. If I wanted to add colors, I could either leave out I could have a clear glaze and just add a color, or I could have an opaque glaze, put the opacifier in, and add a color. So I would take the base glaze, and then I could add a stain to it or an oxide. So I have a note here to the right. I say, important point, the additives create the variety along with the firing techniques. So the point is that I take the base glaze, and they're all going to be fairly similar, but it's the additives, it's the colorants that I put in it, and it's how I fire it, whether I fire it in reduction maybe or oxidation, or whether I do a salt firing or soda firing. That's what's going to give me some of the variation, not the base glaze. Okay? So this example I have at the bottom, Oribe, this is from Hesselberth. Again, here's a pretty simple base glaze, and this is like, related to one of the ones that on the top of the page, similar enough, Custer, Silica, Whiting, Volcanic 3195, but it has the Oribe characteristics primarily because of the copper carbonate. So in this case, the ingredients on top equal 100%, and then I've added, that's what the plus is, plus 4.5% copper carbonate and plus 2% bentonite. So the copper carbonate gives me that nice green color, and the bentonite helps keep the stuff from settling out in the bucket. Next page, Temacus. This is another family of these are high iron glazes, and basically they're generally fired in reduction, and this is basically a base glaze and just a lot of iron oxide. And that's what I said, this actually piece of obsidian looks an awful lot like a Temacus glaze, because basically that's what it is. It's got flux stabilizing glass form. It's a melted glass with a lot of iron in it. So it looks like a Temacus. Well, it essentially is a Temacus that came out of a volcano. So again, really simple, nothing magic about it. It's the high iron that gives us the effects. There's a family of also glazes, generally fired in reduction, called tea dust glazes, and they have little pale green crystals in them. So again, I have a base glaze, and the trick is that crystal is caused by adding a lot of magnesium to the glaze. So the magnesium could come from talc, or it could come from dolomite, or it could come from the chemical magnesium carbonate. And the magnesium forms the crystals, and then I add some iron to it to give it a little bit of color, and that's my tea dust glaze. So the special effect forming these little sparkly crystals is really not from the base glaze, it's from the additives that I put into the base glaze, the extra magnesium and the iron. And I alluded before to tomato reds, the next category I have here. It's a base glaze, and typically I have, in addition to the base, I have iron oxide, and then I have bone ash, and in some cases some magnesium. And the bone ash and the magnesium act with the iron and help bring out that red color to the iron rather than a brown or a black color. And this is a particular recipe, Harris Temaku, pretty basic glaze, nepheline cyanide, silica, dolomite, kaolin, but you notice it has talc in it and it has bone ash in it. So the talc is giving me the magnesium oxide, and the bone ash is the bone ash, and so those two, in combination with the red iron oxide that I add, gives me that redder hue to the color. Copper reds, again, the magic in copper reds is not the base, it's what you add to them. Copper reds, these are reduction-fired glazes that give you these sort of beautiful reds, mahoganies and things. So if you look at the recipe, pretty simple base glaze. Nepheline cyanide, that's a flux. Silica, whiting, another flux. Kaolin, there's my stabilizer. And 3134, that's that frit again, that's kind of a substitute for Gerstley borate. So I've got three fluxes, nepheline cyanide, whiting, and 3134. I like that, balance of fluxes. But now the magic comes from the fact that I add some copper to it, copper carbonate, and some tin oxide, and together they give me that nice, those red colors, those reds and burgundies and sang de berth, as they call them, the blood reds and things. And the red iron oxide just modifies the color a little bit. And again, I've got bentonite to keep it from settling out of the bucket. But again, the base glaze could be anything. It's the fact that I've added the copper and the tin to it that make it a copper red. Otherwise, this is just a transparent glaze. The top recipe, nothing special. Chinos, again, I talked a little bit about Chinos before. I guess we don't have to go over this one because we already talked about it. But that's just basically a simple recipe with the soda ash in it. So let's go to the next one, ash glazes. This is a little more involved ash glaze than just the one-to-one ash and clay. But again, it's, so in this case, I've got wood ash at over 50%. And I add a little bit of whiting, which gives me some more calcium, and a little bit of Custer feldspar, which now gives me a little bit more potassium. So those are my fluxes. Then I've got silica, and I've got my clay. And then I've added, for colorants, I've added cobalt carbonate, which is going to give me a blue, copper carbonate, which is going to give me a green, and bentonite again for the bucket. So I suspect this one somebody has been tinkering with, probably the whiting and the Custer. They may affect the way, and I can't tell for sure, but they may affect the way it melts, or they may affect the runniness of the glaze. This, I'd have to sort of test it to see. But it's still basically a pretty simple recipe. It's nothing that complicated about it. And it's very understandable. It's got three fluxes and clay and silica, pretty much like a lot of the other recipes. The matte glazes that are matte, can be formed in different ways. I can have these elements that are called magnesium, calcium, strontium, and barium. Those are called the alkaline earth elements. And so if I have an excess amount of those in a glaze, they tend to form crystals. A lot of magnesium and or calcium or strontium or barium or combinations of, I tend to get crystals. So this is, if I want a really matte glaze, this could be cone 6 as well as cone 10. I could put a lot of that in it, and it tends to form crystals when it cools, and that gives me a matte glaze. I can also get matte glazes by adding a lot of silica, essentially too much silica to the glaze, and I can get a matte glaze because it doesn't melt and doesn't become glassy. So it stays kind of granular looking, and I can make or even too much alumina, I can make a matte glaze. Now the difference is, with all three of these approaches, the effect on the color is going to be different. So if I was going to make a pale, a matte green glaze, if I did it by adding magnesium, I wouldn't get the same shade of green as if I added excess silica or if I added excess alumina. These are just three different routes to doing it. Okay? So diagnosing problems, and I've got 3 examples here that we'll wrap it up with, and then we can take some more questions if there are any. But here's some good examples other than the ones I mentioned already. This first number 1, this is a glaze. Somebody sent me an email and said that they got this recipe, I think from online, but I forget where they said, but they said it just didn't seem to melt right. So let's look at the recipe. Rutile 25%, feldspar 25%, whiting 25%, and ball clay 25%. And this was supposed to be a cone 6 glaze. So what do you see about the glaze? Rutile? Yeah. Yeah, rutile doesn't melt at cone 6 for one thing, very easy. But also, there aren't any low temperature fluxes. There's nothing in here that's going to melt easily. Feldspar doesn't really even melt at cone 6. So there's nothing in here that's going to melt at cone 6. And rutile, that's a colorant. 25% rutile is a lot of rutile. That's a lot. Normally you might add 6 or 8 or 10% maybe. That's a lot, but it doesn't melt easily. So I've got, and feldspar will barely melt, whiting doesn't melt at all, and bald clay won't melt at all. So I hardly have anything in the recipe that's going to melt. So yeah, it's not surprising that the glaze didn't melt, because there's almost nothing in it that would make it want to melt. This wouldn't even melt at cone 10. Okay, so again, just the minute, so I asked the person, I said, well, send me the recipe. You know, the person described it, and I said, well, send me the recipe. Sometimes it's hard to diagnose things, you know, just without on an email or something. But the minute I saw this, I didn't even have to get up from the keyboard. I could just say, well, here's the reason why, you know, because there's no way in the world this is going to melt. So this is a good example. This is a really bad recipe, and yet it was being passed around, and apparently the friend of the person who sent it to me claimed that the friend had gotten really good results with it. I don't know on what planet, but because there's no way that, unless, you know, they've done something different, there's no way that this can work. Here's another glaze, eggshell. This is a recipe for eggshell. So whiting, 9.5%, zinc oxide, 5.5%, bentonite, 7.5%, EPK 5, silica 8, ferrofrit 3124, a lot of frit. And that's normal because this is the cone 6 glaze. So I've got to have a lot of something that melts at a low temperature. Custer feldspar, and then plus tin oxide, which is an opacifier. That's going to make it opaque, and red iron oxide. So the iron oxide is going to give it a brown tan color, and the tin, along with the tin, which is white, is going to give it this sort of tannish brown color. But now when I look at the recipe, what is there something that stands out to you? Bentonite. 7.5%, way too much. And in fact, what happens with this recipe is when you put it in the bucket, it turns into pudding, and then it cracks like crazy when it dries. So you can just look at this recipe and say, this is going to be a real problem. So what I do is, when I made up a recipe like this, it was similar, I just reduced the bentonite by about 5.5%. And it works fine. But again, you know, why would somebody do that to the recipe? I don't know. Because the bentonite is only there to help the processing. We don't want it as part of the final glaze. It's not doing anything for us. It's just to help it in the bucket. So why in the world would you have 7.5%? And even then, if you notice also, I haven't even tried to add this up. Even if you're adding bentonite, it shouldn't be included in the top. It should be at the bottom with the tin and the red iron oxide. That's the way it should be listed. But so I have no idea. But anyway, so the minute I looked at that, you know, and in fact, it does do what it advertises that it does. It gets like pudding in the bucket, and then it cracks when it dries. And as a side benefit, it crawls when you fire it. Okay, so the last example I have here, this is a cone 6 glaze, and it runs a lot. And somebody said the same thing. This is another question I got. They said, well, here's a recipe, and I like it, but it runs a lot, even at cone 4. They said, it's a cone 6 glaze, and it also settles badly in the bucket. What's wrong with it? So what's wrong with this recipe? Superpax is another opacifier, by the way. That's like Zircopax. So what's wrong with this recipe, for one thing?
Lithium.
Pardon?
The lithium buffalo.
Yeah, but what else? That's true. There's no clay in it at all. Where's the stabilizer? So, like, gee, no wonder it runs, because there's no stabilizer. There's no clay at all. So, yeah. Okay. Now, the lithium is a powerful flux, but and you've got 3124, which is another source of flux. So I've got 3124, which has calcium and boron and lithium. The lithium is in there probably because with the copper, I'm going to get a certain shade of blue. I could have used other fluxes, but I'm going to get sort of a turquoisey blue out of it. So that's not really a problem, but the real problem is there's no clay in there at all. So with that amount of stuff, I should have 20% or something of clay in there as a stabilizer so that it doesn't run. So it doesn't get too runny at cone 4. It doesn't run. And then the clay would also help keep it from settling in the bucket, because it settles quickly because, again, there's no clay. So if I have a recipe that has a lot of clay in it, then I don't need bentonite as well. You'll also see a recipe that'll have 20% clay, and they still add 2% bentonite. I guess out of force of habit. You don't need to. because if you have that amount of clay, enough clay in the recipe, that will help the settling. You don't need the bentonite as well. It's when you have a recipe that has low clay that you might want to add a little bentonite to it to help prevent the settling. What this is intended to show, thank you for that, Jane. This was intended to show that I think I made this point, but this is supposed to emphasize that some of the fluxes that we use only give one flux, and some of them provide other materials. So like whiting, dolomite, wood ash, soda ash, and the borates, those are only fluxes. But now when I add potash feldspar, that provides a flux, but it also provides aluminum oxide, and it also provides some glass former, because that's in the chemical formula. Similarly for nepheline cyanide, I use it because it contains the flux, but it's giving me some aluminum oxide, and it's giving me some silica. The same way for the spodumene, it's giving me some lithium, but it's also giving me aluminum stabilizer, and it's also giving me some glass former. Now the talc, that's the formula, magnesium silicate, it's giving me flux, the magnesium oxide, and it's giving me silica, the glass former, but it's not giving me any stabilizer. And the clay is giving me stabilizer and glass formers, but no fluxes, and the silica is only giving me the glass former. So, thank you. And the reason why you might say, well, why do I use these ingredients that contain the other stuff? Because at least they're things that are not going to hurt me, but when I calculate or work out a glaze, I have to keep that in mind. So when I add feldspar, because I want the sodium, yes, I'm also getting some aluminum oxide, and yes, I'm also getting some silica. So I can't add as much silica or aluminum oxide as if I didn't have any coming from the other ingredients. I have to take all that into consideration, that I'm getting these other things from the ingredients. But as I mentioned earlier on, I wouldn't want to use pure sodium oxide. That'd be great. I could just weigh out pure sodium oxide, but in this case, it'd be expensive and dangerous. And there are some other materials that simply aren't available or too expensive. So I use these combined ingredients because they're available, they contain everything I want, and they're not too expensive. All right, well, thank you very much for coming. Appreciate you all coming.
The Potter's Roundtable is brought to you by Washington Street Studios and our patrons. If you enjoy the show, please subscribe, give us a 5-star review, and tell your friends. If you want to learn more about Washington Street Studios and shared studio memberships, please visit our website at www.hfclay.com. Thank you, and we'll see you again next time on the Potter's Roundtable.